I have an omnidirectional mic. If you don't know if your questions have been heard, then that means you didn't watch any of the recordings. All right. You had to review, you had a midterm, right? All right. So we're going to play a answer questions, get candy type of lecture. So that should be super fun. I'll just stop asking questions. That's the key. Cool. All right. So we looked at basically what we're talking about now is network security. And we've been talking about the networking stack, specifically around TCP/IP. And we talked about kind of the physical layer, which we're going to ignore a little bit because we don't really care. I'm not an electrical engineer, so I don't really care how my data gets from one point to the other. I just care that it gets there, or that the link layer can handle that. So the link layer has our actual physical hardware interface. So this is dealing with MAC addresses. So your hardware interface will have a MAC address, which is something that we're probably, hopefully familiar with. Above that, we have the internet layer. So we have the IP protocol. I guess that's technically redundant, but we have the IP layer, and then above that we'll have either TCP or UDP, and finally above that we'll have our applications. So, cool. So then what's the purpose of ARP? That's where we stopped last week. Yeah?
Doesn't ARP translate MAC addresses into IP addresses?
Why?
Because that's what it was designed to do.
Sorry, I don't want to hit anybody. This is the problem. And apparently like 6 Sour Patch Kids aren't enough of a heft to really throw. All right, so let's look at ARP. So we looked at where we were. There we go. So we looked at ARP, and basically, so what we looked at is so if 2 hosts are on the same physical network, so how would 2 hosts, so A, how would 2 hosts know if they're on the same physical network?
Network ID.
The network ID, how would it use that? So you're host A, you have a certain IP address, and you want to talk to host B. How do you know if host B is on your local network or not?
When you check the network ID, see if they each send it off.
Yes, using what? Like how do you check the network ID? How do you know what is the network ID?
By the subnet mask.
Yes, boom. There we go. Nice, it's a lot easier if you're closer. By the subnetwork, right? So either the subnet mask or the CIDR routing that we looked at, that will tell you how much of the prefix that we need to use in order to tell if we're on the same network or not. So here we have 111.10.20.121 that wants to talk to 111.10.20.14, right? And the key problem here is that as a user, well, we haven't talked about DNS yet, but as a user, essentially, we know we want to talk to that other IP address. We know also that it's on our local network. But we don't know what's the physical MAC address of how do we actually send a packet to that machine because it's on our local network. It should get that. It should get it. So that is where ARP translation, where ARP comes in, because this packet from 121 to 114 has to be encapsulated in a link layer packet that has to have the MAC address of the other computer. So essentially what ARP does is allows this translation to happen of translating IP addresses to MAC addresses. Cool. And we saw this example where we actually looked at some traffic and we saw that we could see the ARP request and the ARP reply. So how this is actually done is at the link layer. So that's why in that other diagram we just looked at, the link layer has ARP in it. Although, like I mentioned, today, Tuesday, so on Thursday, that's it kind of blurs the layers, right? Because it's technically at the link layer, but it's translating between the IP layer and the link layer. Cool. So now that we've looked at this in a technical perspective, right, one of the things we always want to think about is look at things adversarially, right? That's kind of something I want you to be thinking about in this class, right? So think about what host A knows. So let's think about from host A's perspective. So host A wants to talk to 192.168.1.10, right? That's a given. Host A knows that. So host A does what in order to do the ARP translation? Yeah.
Yeah, everyone who is 192.168.1.10.
Yes. By sending out an ARP request, right? So host A sends out an ARP request to every single host in the network. How do we know that this packet goes to every single host in the local network? Yeah. Because the destination MAC address is all ones. Oh, sorry. Right? So now, host A gets a reply back. What does host A know for certain at this point? Something replied. So it knows that it got a reply to its initial request, right? But does it actually know that this packet was sent from host B? Why not?
It could be for it could have the same address that was like it could say it actually is it, but I have no actual idea that it actually is what it says.
Right, so when we looked at the types of Ethernet frames, I guess I didn't make a diagram, but the destination can be controlled by the attacker, the source can be controlled by the attacker, the type, basically the data, everything in here can be controlled by an attacker. There's no authentication, there's no guarantee that this is actually coming from this MAC address. Here, you want a star patch? I'm gonna try to frisbee toss it in the back. Sorry for heads. There you go. Thanks. That almost worked. All right? So when we get this reply back, host A actually doesn't know for certain anything, right? All it knows is it got a packet that claims to be from this MAC address to its own MAC address. So probably can't spoof, I mean, it probably doesn't make sense to spoof the to MAC address because otherwise host A is just going to discard it, right? It's not for it. It has to be addressed to the right person. And it's saying, hey, 192.168.1.10 is at 0131D98D8. So, and this is, the other thing to keep in mind is this is baked into the core of these protocols. There is no authentication, no authenticity about this packet. And so as adversaries now, we can use this to our advantage. So what type of things could we possibly do? It's going faster than I thought. You already answered. Yeah. He's not your friend, he just stole your question. No, sorry. Go ahead.
You can impersonate, it's pretty much a change your authentication. You can't, since you can't authenticate, you can be whoever you want to be, say whoever you want to be.
Right, so you could forge your own ARP reply, right, to tell the host, hey, host B is actually me, not actually host B. So let's see if we can do this over it. Oh, right in between you two, that was perfect. Should have fought over it. So we can impersonate a host on the network, so we can pretend to be something else. What types of things would we want to be as an adversary? What our goals would we want when we're on a local network? So wait, let's take a step back a little bit. Chocolate this time. What are the threats? Like what scenarios would you worry about a local area network attack? What does the adversary actually have to do? Yeah.
You have to physically plug into the network and then pretend to be something that was already there.
Right. So they need to physically, well, possibly physically plug into the network.
like.
Or what else?
But they have to be able to authenticate to your network if they're going to do it over Wi-Fi.
Yes, so they either need to be physically connected to your network, logged into the same to the same wireless network, or what else could they do? So there we go, getting better at this. Are those the only ways that somebody could get onto your network? So if you prevent, let's say you glue every Ethernet cable into one computer and into the other computer, and you're using like titanium, or if you want to go crazy, like, I don't know, fake adamantium cabling, so that nobody can actually cut that connection, and all of the Ethernet ports are actually filled in except for the ones that are connected. Are you safe? Do you not have to worry about a local area network attack?
Like if you have a network gateway,
Mm-hmm.
they could get it with a gateway. I mean, I guess that's Wi-Fi. I don't know.
Yeah, that's one.
USB. There's some way to get into the USB, but they can even interfere with the actual transmissions.
Ooh,
And it would
what
be some way.
It's
transmissions
completely
that-
shielded. It's 100% shielded cable. Yes, it's
Really?
super awesome cable. Yeah.
Maybe more physical, and I don't know if technically the example is possible, but you could slice it into the Ethernet cable.
You can't cut the cable. You can't cut into the cable. It's impossible to open this cable.
You just break the router.
You can break the router. The router's behind like arm guards. Yeah.
They can't just compromise a host that's already on the network.
Why not? What would that mean? So how would you do that?
Overflow, you inject some malware, some Trojan horse, some backdoor, some rootkit on the machine that's already on the network.
Or just trick them to download, say this is the corporate earning reports, execute this file, and somebody in the network will download it and execute it on their machine, right? So if we can do this, oh, that was wrong. Well, I can make it play back there. Right, so that's the key problem here is that, so when we think about hosts on the network or local area attacks, we typically always think about physically, you have to be physically close. But actually, all you need is control over any node on the network. And that can either be by injecting yourself as a new node on the network, or by compromising and taking over an existing node on the network. So this is kind of the key, one of the key issues here. So what else might we want to do if we were an attacker on the local network?
Monitor all the data and traffic.
We might want to monitor all the traffic, right? We might want to, you gotta have better reflexes. Yeah, we might want to monitor all the traffic on the network, right? To see what's happening. Yeah.
Eventually open up other holes in the network that you can get in using other machines.
Yeah, so we may want to, sorry, that was a weird throw. So yeah, we may want to open up different holes on the network. We may want to add persistence to our network. So what are some of the other, so we talked about basically, we can kind of, you can think of it as we can take over the integrity of the system by impersonating a node. We could compromise confidentiality by sniffing and spoofing on traffic. What else could we do? Yeah.
They could use the network for another attack on something else.
We could attack something else. What else could we do? Well, yeah.
You just flood the network with traffic.
Yeah, we can perform a denial of service attack in the network. And maybe we can take down, so this would be if we're maybe robbing a bank, we could take down their security systems, or their alarm system. I'm sure their alarm system probably uses the internet because it's bad. Or some systems, I'd say, probably do. So yeah, you know, taking hosts down is actually really important, or can be really important. You know, all these types of things. So we kind of think of it in terms of like sniffing, spoofing, and hijacking are some main goals that we want to accomplish. We want to be able to sniff which means read the traffic that's happening on the network. We want to be able to spoof packets and pretend to impersonate nodes on the network. And we may want to even hijack connections between two computers and inject data into them. What's the difference between a hub and a switch? No, you already answered. Let me think. So I'll say on the first thing, they're both networking devices. Right? They're both used to route traffic, usually at the Ethernet level. Yeah.
Could be wrong. Switches
Be wrong,
essentially take input and then kind of split out, while a hub takes multiple inputs in and sends it out as one.
Very close. Very close. I'll allow it. Do you want a refinement in the back? Huh? Yes, so hubs are incredibly dumb. So whenever a packet comes into a hub on one of its ports, it retransmits that packet on every single port, right? So you gotta think about like a physical, you guys have seen like big switches, right? With like just a bunch of Ethernet ports on them. So for a hub, any packet comes in, that same packet goes out on every single port. Whereas a switch is slightly smarter, because a switch keeps track for every physical port. It sees what ARP replies have come back from that port, then it maps MAC addresses to ports, and that way, if a packet comes in destined for a certain MAC address, it only sends it out on the ports that it's seen that MAC address. Does that make sense? And if it hasn't seen it, it will just broadcast it, I believe, to everyone. So basically the early networking switches are simple hubs, and you gotta think, well, this is a lot easier and cheaper to build, so I'm sure you can get these pretty cheap. So basically all broadcast traffic, so all packets that are sent as the destination of FFFFFF, right, all ones, that's sent to every connected host. Otherwise, it keeps track in its routing tables of which MAC addresses are associated with which port. Why is this important to us? Is this just a random technical detail that I'm throwing in? Yeah.
Well, if you have a hub and I've infiltrated your network, you can impersonate one of those hosts, and it's broadcasting whatever you're sending out everywhere. It's easy to pick it up.
Yeah, not even impersonate. You just sniff, right? You don't even have to do anything. You just are plugged into the network. And by virtue of that, you're getting every packet that's being sent on that network, right? Whereas if it's a switch, you would not have that by default. Cool. So many, and this is important, yeah.
What would we ever use it for networking? The only way I can think of it is use it in point A to point B, and there was just a few difference. So we use
I think mainly because it's cheaper. Like if you buy like a 4-port switch, it's usually $10 cheaper, I think, to get a hub or something. So oftentimes you just choose a hub. So for like a 24 or 48, so what's the main like technical problem of one packet comes in and you repeat it on all the other ports? Useless information. You may actually saturate the bandwidth, right? The larger and larger the switch becomes, you have 24, 48 ports, right? You can only send out, the entire network is limited to how fast you can broadcast kind of on all of those ports. Whereas with a switch, it can be much more efficient, right? It's only using those things, but it adds more processing capabilities. It has to actually keep track of these things.
Makes you like accidentally DDoS yourself on a hub. Like if you were just basically, if you had like 4 computers on a hub, you said I need to download a 4 GB file from the internet, and it's like then all 4 of those computers are now getting those packets.
Yes, it would, but it would. I mean, assuming you're downloading it from a remote source, it's not going to be, like your upload link is not going to be enough to saturate your local area network. But when you start, if you're trying to say like you have these 4 computers and you're trying to transfer like a 40 gig file from A to B, and then a different file from B to C, and then another file from like C to D, that's gonna like completely degrade the quality of your network. So you're like I would worry more about the inter-network speed rather than like an external transfer.
So you couldn't possibly accidentally, like, say, if the computer A and computer C are sending packets down the hub, and somehow they accidentally mix the packets up.
No, we'll get into that. There's actually a mechanism built in to prevent infinite packet transmissions. Although, can you? No. Anyways, okay. Yeah. We'll see kind of a slight instance of this. Because the idea is this, so the technical implementations of these networking devices that establish a local area network impact how we can perform sniffing, right? Which is what we talked about. And really, as we'll see, sniffing and being able to observe network traffic is a key to many, many network attacks. And it's disgustingly easy. So if you've never done this before, this is part of why you're taking this course, so you can learn how easy it is to do these kinds of things, so you can think about being more safe on the internet. So all you have to do is set your network. So by default, your network interface card will only send you packets that are destined for your MAC address, right? Because it's filtering out, it knows its MAC address, it sees packets comes in. If it's on a hub, it'll just ignore everything else. But of course, it's got a mode that you can set easily called promiscuous mode that will return every packet that happens there. And if we're on a hub, this is it, we're done. We've changed our networking mode to promiscuous, and now we're literally getting all of the traffic, the network traffic that's being sent across the network, right? So our sniffing job is done. But if we're on a switch network, what do we have to do? So let's think about it in terms of pretty pictures that I'm going to finger because I didn't get the thing. All right.
If it's the switch, do you have all the MAC addresses?
Possibly. Maybe not all. It kind of depends. So let's do a super. So this is going to be a 4-port switch. Right? And they all are connected to something. Real switches don't look like this. All right, cool. So we're here, we're the attacker, and we have computer B and computer C here, and computer B has a MAC address of, somebody give me a 2-digit hexadecimal. You're too slow. I'm gonna do 1, 2, and I'm gonna do 2, 3, because I think these are gonna be easier to draw. Cool. So B and C wanna talk to each other. They've never talked to each other before. So host B maybe pings host C, right? What's the first thing that happens from host B's perspective? ARP request. So host B sends out an ARP request. That request gets to the switch. Where does it go? Everywhere, because it's a broadcast. It's an ARP request. It's broadcast to the entire network. So it gets sent out on every single connected port. Host C sees that request and does what? Says, hey, that's my MAC address. And then does what? Replies and says, hey, 1, 2, host C is 2, 3, right? And it will send that out. So what actually happens to the switch then? What happens to that? So to that packet? So
It's added to the table.
it gets added to the table. So it's inside the router. It's going to keep a table that says, hey, I've seen MAC address 2, 3 on this port. And we didn't talk about it, but because I forgot. But host B, when it sends the request, it's saying what MAC address it is. So it will usually, I think we'll keep track of that then or later. It doesn't really matter. So that way when host C does its ARP reply, it replies to what MAC address? 1, 2. So then where does the switch send that out? Yeah, only to the port where 1, 2 is. Sorry, you guys getting candy hungry? You already have one, you already have one. All right, somebody else answer so I can get rid of this. Otherwise, I'm just, yeah. Right, so it only sends this packet out to host B, and now host B and host C are going to communicate over IP. All of those IP traffic is encapsulated in a link layer frame, which has the destination of 2, 3 if it's going from B to C, or the destination of 1, 2 if it's going from C to B. And therefore, the switch, because of these mappings in here, will only send those packets out on those ports. So if we are the attacker and we connect and we just put our switch into promiscuous mode, what types of packets will we get?
ARP request.
ARP request or any other Mac broadcast request, right? Because they get broadcast to the entire, to every single port. We'll get those, and if there's any that are destined for us, whatever our MAC address is, then we'll get that, but we're not actually in this network, so we should not be getting any traffic, right? So, we do not like this situation. We want to get their packets. How do we do that as the attacker? Yeah.
Be the first one to respond to any requests and just tell them that you're everything.
Yeah, so I'm going to say that our MAC address is 3.4. So there's a couple ways we can go about this. So one way would be if we wanted to snoop on this traffic, B is going to send out, hey, an ARP request, hey, I want to talk to host C. We get that and we reply with what? What?
I'm host C here at 34.
Yeah, I'm host C at 34, and then this switch will do this. We'll add 34 to its route, or sorry. Okay, there's two different ways we can do this actually. Sorry, let's step back. So, there's already a communication between B and C. What we can actually do most times with most switches is actually just make a fake ARP reply to nobody that says, hey, I'm 23. And nobody else will listen to that maybe or get that, but the switch thinks that the MAC address is on that port, and so it will send the traffic to 23 to both ports. Another thing that we can do, so this is when we get into the switch versus hub things. The switches fundamentally have a limited capacity, right? Think about it's a limited physical piece of hardware. There's a limited amount of memory to do each of these mappings. So we just send a bunch of ARP requests or ARP replies with different MAC addresses, 1, 2, 2, 3, blah, 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 until we fill up this table, and then the router goes into an oh crap mode. There's too many MAC addresses to keep track of, so it just sends every packet to everywhere. It basically defaults into a hub, right? Which makes sense if you're designing a switch because you want to design it in such a way that it will fail open and everything will still work, even if you plug in. Because one thing to remember is this could be a host or it could be another switch, right? And that other switch could have 40 or 80 or 200 hosts on it. And so that port, it's not a one-to-one mapping between MAC address and port. It could be multiple MAC addresses here. Cool. So
Only certain manufacturers that attack works on, like specified here.
I don't know. I'd have to do a little bit more research on that. I don't know the current state of router security. I would imagine that nowadays memory is pretty cheap, so it would be more difficult to do this, but I'm sure it's not impossible. And so there's some other tricks that we can do, which are super cool. There we go, with the eraser. We can actually, so one thing we can do is there's a tool called ARP Ping, which will try to do like a ping that'll try, basically we can try to figure out who's on our network by sending an ARP ping to all of the Mac machines and see if they respond to us. So this way we can see that, hey, there's host B which has MAC address 12 and host C which is MAC address 23. Then what we can do, so oftentimes so when we think back to the link layer, were there any guarantees about delivery or that things would get there or that messages wouldn't be transmitted multiple times? No, there are absolutely no guarantees at the link layer, right? Packets can get lost if the switch gets overrun. You have absolutely no guarantees. So because of that, oftentimes what we can do is we can actually just spoof all right, so this is the ARP table of B. Oftentimes we can actually just spoof an ARP reply as if we were C to change the MAC address to 34. And it will just update its table even though it never actually made an ARP reply. So rather than actually keeping track that it made these replies and it's getting responses, so we can, as A, we can send a packet that says, hey, I'm C and I'm at 34, and then we can direct that to B, and then we can get that, and then it will, oh, that's not the color one. Yeah, it's a lot harder. It will update its ARP table so that now all packets, when B wants to talk to C, it will actually send all the packets to MAC address 34, which go where according to the switch.
According to the switch, right?
According to the switch. Yeah, it goes to the port that A is connected to, right? So we're getting all the traffic from B to C is going to us. So this actually allows us to completely impersonate C. We can reply with whatever we want, and B will think that we're actually that IP address, and we'll have no idea. So this is how we can impersonate another host on the network. We can actually go even further because now, right, we're not actually eavesdropping the communication between B and C because we're literally taking over host C. So if we wanted to try to just listen to the traffic between B and C, what would we do? How can we do that? Yeah.
Could you say that you're C, but then when you get input or you get something that was meant for C, you then forward it to C after receiving it?
Yeah, so because we know the real C, we know the real MAC address of C, so we can actually take that packet that we get from B, right? Take that data packet, take it, send it to C, right? We'll obviously record it or whatever, store it, but we can take that, send it to C, because we know that C is at MAC address 23, so we just change the frame, and it goes out, when it comes into the switch, it only goes out on the port that C is attached to. And then now, but what happens now when C responds? It's going to respond to, well, so think about the packet. So we got to think, remember, because there's layers, right? So in our outermost link layer, we have, so the source is 1, 2, and the destination is 3, 4. Right? Because we've tricked B into thinking that 3, 4 is IP address C. But now inside the IP layer, what's the source IP address? B's IP address. And the destination IP address? C, because this is a packet from B to C with then some other layer of some kind of data that we don't care about. Right? So this is the packet we get from B, because we've intercepted this, right? So what could we do? Well, we can take off the outer layer. This is surprisingly good. Oh, I got too full of myself. Okay. From 34, so from us to 23 is going to be the new layer. But what are we actually going to put as the packet here? Do we change the source IP from B to A? What would that mean if we did that? Yeah, we'd be changing the IP layer. So from C's perspective, when it gets this packet, it thinks that the adversary is trying to talk to it, not host B. Right? So there may be an IP trust relationship here. C may have something like, if somebody logs in from IP address B, then don't ask for a password. Right? It may respond differently. and we're trying to transparently man in the middle of this conversation and sniff all the traffic of this conversation. So if we change the IP packet, we're going to completely change the semantics of this conversation. So we want to keep actually this entire packet exactly the same. So let's see if I can visually represent this in something that makes sense. So this is like exactly the same packet as we have here, right? So then when C gets this, what is it going to respond to? Yeah.
Respond back to 34, right?
I guess the answer is more it depends. So it actually usually doesn't look at the MAC address because you don't really care at a higher level what physical host you talk to. What you care about is what IP address did this packet come. Close. What IP address did this packet come to so that you can reply back to that IP address. So using that logic, then who's it going to try to respond to? IP address B, exactly. And how does it know what MAC address to use to talk to host B? Say it again? So usually, well, okay, it may do that, but it usually doesn't. It all depends because it always goes back to the ARP table, right? So C will have its ARP table. So the question is, it wants to send a packet to B. What is the ARP table entry for B, right? So it may do an ARP request and say, hey, who has IP address B? Now as the attacker, now what do we want to do? Spoof it and reply and say, we're B, right? So that in its ARP table, hardware address 34 is mapped to B. So now whenever these two machines actually want to talk to each other, the packets will be routed through host A, or adversary, right? So whenever C wants to send a packet to B, it will actually send it to physical address 34, which will only go out on this port, and then we take that, do the same translation we did, send that back to C, host B, and then the response comes back to us, and we can do this again. Anybody ever admin a network where you have too many devices on, like you have a subnet that's only like 128 and you have more than that many machines? Like DHCP runs out of addresses and it starts reusing new addresses? No, it's super annoying because this happened in our lab and I would SSH to machines and like sometimes it would work and sometimes I'd get like the server key doesn't match, like you're not allowed to log in, and it was super confusing until you like would trace the network, do a bunch of ARP pings to see what everybody was, and you'd see that for that IP address you'd get 2 different ARP replies. By default, your computer does nothing about that. It doesn't give you a warning. It doesn't like warn you that the network is weird. It just like things barely work. So as an attacker, you can use this to your advantage to man in the middle traffic, to snoop on traffic, even in a switched network. Cool. All right. So this was all about this third bullet of if the switched Ethernet is used, then we need to try to convince the switch that a copy of the, so we can convince it by just pretending that we are the MAC addresses we're interested in so we get their traffic. But if we want to actively man in the middle of them, we can do that by poison, as we'll see, it's called ARP table poisoning. So we basically poison the ARP tables of the 2 hosts to have them direct traffic to our physical address. Okay. So sniffing is actually incredibly effective. So I should probably do this at some point. Oh, that would be a good exercise. I'll just put up a Wi-Fi network and sniff all the traffic that you guys who connect to it send. So this was very true at the dawn of the internet, and it's still even true nowadays that a lot of the higher level protocols, FTP, POP, HTTP, IMAP, all actually transmit information in the clear, including your authentication information like your username and password. So this is why if you are logging into a website and the login form uses HTTP and not HTTPS, literally anybody in your local area network could get that information and that password, which is why, and so you can do this, and this actually happens a lot. So when I was doing a pen test of this credit card processing company, we had just a tap of all the traffic coming out of that network. And so we listened to it for like half a day and then ran a program on it to detect if any of these authentication information. And of course, there was some, I think it was a marketing person who'd set up a marketing website and was using FTP to connect and upload files. And so we were able to get that username and password, log in, and upload our own like malicious software to their domain. So it gave us a foothold into the network, all because this is transmitted essentially in the clear. And sniffing is incredibly easy. So there are lots of tools that you can use to collect, analyze, and even replay traffic back. They're actually incredibly handy to use even in a non-security context. So if you ever do any network administration, being able to use things like TCP dump and Wireshark will get you out of a lot of jams and will make you look like a rock star usually at your job if other people don't know how to do that. I had an issue with, not this, it must have been maybe a couple years ago with like a 545 class where I had a web hacking assignment and I was trying to break through the levels and I'd send a request and it would just hang. And because I was running this in our lab, I didn't know where the problem was, right? And so I had to TCP dump like the actual machine, like nope, no request there. And then I'd TCP dump the our network gateway and I didn't see the request and I'd TCP my computer to see like TCP dump to see that yes, the request was getting sent. So I was able to deduce that it was a stupid network firewall that ASU had used. And so I just put it behind HTTPS, which encrypted everything, and now the request went fine. So only by like using these tools can you debug that. So TCP dump is a very handy tool to collect traffic. You can write it out to a file. It can show you the summaries. TCP flow is a nice one that actually, as we'll see when we talk about TCP, it reassembles flows. You can replay things. Graphical tools, Wireshark is actually really handy for digging into network traffic. So usually kind of my flow for this is like I'll use TCP dump to actually capture the traffic to a file, and then I'll copy that file to my local machine to use Wireshark to analyze it, because Wireshark has a nice graphical interface and it parses the raw packets. So you'll see, okay, TCP packet, TCP packet, TCP packet on port 80, and then you'll see that it actually identified it as an HTTP request. And so it gives you the whole high level protocol for a lot of different protocols. Cool. So I recommend you play with these. So ARP spoofing, as we actually just saw, we can go through this very quickly. So this was what we just derived as a group, this is how we can sniff all traffic between two hosts in a switched environment. Oh, sorry, just a second. I want to talk about why sniffing. So this is actually one of the core reasons why using a public unsecured Wi-Fi network is so bad. So have you heard that advice? Yeah. The reason is because anybody on that unsecured Wi-Fi, so if you're at a coffee shop and you connect to an unsecured Wi-Fi, anyone in that network can have a Wi-Fi card that's in promiscuous mode sniffing your traffic and seeing all the packets that you send. This is not possible in an encrypted or password protected Wi-Fi network, so you're secure there. It was Jamie Winterton, is the strategic director of the Global Security Initiative, had a really good analogy where she said that like using an unsecured Wi-Fi network is like going to a public restroom without any shoes on. It's really, really gross, but we don't actually feel or think of it that way because it's digital. But that's what you should be feeling and thinking, and you should be much more aware whenever you have to do that. So, and there was, so Facebook used to be HTTP most pages, but HTTPS login. But when we get to the web, we'll see that web requests have a cookie that gets sent. So you're probably familiar with cookies that actually link all of your requests together. And this cookie was sent over HTTP. So I think it was called Firesheep was the name of this tool, a graphical tool that would sniff all the traffic on your network, look for any HTTP connections to Facebook, steal all those cookies, and then with like a one-button click, it could log you in as that user on Facebook. And you could start browsing as them. And Facebook switched over to HTTPS everywhere very quickly after that. Yeah.
So there's an add-on for Chrome called HTTPS Anywhere. Is that actually like?
I think it's HTTPS everywhere. The idea is I believe it always tries HTTPS first, but it still has to have the other end supported. If the other end doesn't support it, then there's nothing they could do.
Yeah. So I was thinking the website itself is not HTTP. Like maybe you send an encrypted message to it, like.
Yeah, exactly. Even and yeah, I mean you can get into weird things. Like technically you could, if another host was impersonating them, you could like tunnel the traffic, but you get into a lot of problems there. Please.
I got a question.
Sure.
You said Facebook kind of made that change, but you still kind of hear recently people talking about Facebook accounts being kind of breached.
Mm-hmm.
Is it when Facebook? So I don't know from your knowledge, from saying Facebook patched it, does that mean even like when you see people where they're like, you click on an article and it's like, oh, click here to this link, and then it like tries and it asks like you to log in your Facebook credentials, and it's still trying to use like an HTTP site that like someone was still able to post through Facebook through like an intermediate link. I don't know if that makes sense. Or
So there's a couple ways that people can compromise your Facebook account. So it's all about credentials, right? So we talked about authentication. All they need to log into Facebook is either your username and password or maybe this cookie. It's much and must. They've increased the security essentially. You can think of as the cookie, so it's much harder to get. But there are a lot of ways. So there's a lot, there's actually was scams. There were like copy paste scams. So if you copy a snippet of JavaScript and execute it, paste it into the URL bar, that JavaScript will execute on the page. And I think for a while, Facebook had it so that JavaScript could access the cookies. So somebody would be like, oh, check out this crazy new Easter egg in Facebook. Like copy this blob that's with a lot of percentages, paste it into your URL bar and see what happens. And people would do that and it would be JavaScript that was malicious, steal their cookie and send it to the attacker so they could log in as them. Other things to do is I would create a domain like Fakebook or Flaithbook or something and send you links to it. And when you get to it, you'd see the Facebook login page just like you always see. And you would just type in your username and password. And when you click submit, instead of going to Facebook, it's going to my servers. And then I redirect you back to Facebook. So now you're on Facebook's actual site. And it just says like, oh, you think like maybe the login didn't work. So you'd log in, get in, and it'd be fine. But an attacker has your username and password. So that's a phishing attack is that type of attack. The other one would be, to be honest, I'm not 100% sure how valuable a Facebook account is, like how many dollars it sells for on the black market. But the other way would be like we talked about a compromised local machine, right? If I trick you to execute code on your machine of my choosing, I can have that code watch your internet traffic, watch you log into Facebook, see exactly what you type in, take all that, and then send it to me, right? So I can steal your Facebook account, and there on your computer, I can steal basically any website's username and password that you visit. So that would be kind of the third way.
Now, when you mentioned cookies, let's say they get a cookie, but you change your password after, does that cookie then expire, or even if you have changed?
It depends on Facebook's policy. Usually, yes. I would say I believe they should expire your cookie at that point. So yeah, but you have to think, I mean, so yeah, I guess the answer is yes, they should. I don't know whether they do. The lifetime of cookies is an interesting problem. Yeah?
Would there be vulnerabilities if like someone was using the OAuth system on an unprotected website but do login? So if you had like an HTTP site that used OAuth login through Facebook, would there be vulnerabilities in just scraping the OAuth token and using that for remote login?
Yes, but I believe Facebook can check. Because Facebook, the way OAuth works, one of the ways is Facebook has the endpoint where it sends your token to, and so they can ensure that it's an HTTPS endpoint. So I think OAuth should be okay there. What I'd be much more worried about is a phishing page on OAuth. So actually, as we'll see, I mean, as we just talked about, well, as we'll get to with like ARP spoofing and these kinds of attacks, you can actually inject replies into the connection. So I can, if you go to google.com and it's not encrypted, I can actually reply back faster on your local network with, yes, I'm google.com, here's the web page, but it's actually a login form to my page, and it literally looks like it came from google.com. Like it doesn't, the URL bar, it's not me spoofing the domain, so all kinds of bad stuff. So ARP spoofing. So we have our host A, host B, and we are host C that we want to sniff. So we have the ARP tables here of each of the hosts. So we actually have host A and host B know about each other and have their ARP tables are all complete. Host C also knows from observing traffic what these what the actual ARP tables are. And so we actually spoof replies to both host A and host B that say, hey, actually .10 is now at this MAC address. And host A goes, cool, updates its ARP table. We send a similar packet to host B, but with .100, which is host A's IP address, and it says, cool, updates its ARP table. And now whenever host A wants to send a packet to host B, it actually sends it to host C. We'll take that packet, send it off to host B, and we've effectively man in the middle, and we're intercepting and sniffing now all of their communication between A and B. And to actually do this effectively, most tools will just continually spam the network with ARP replies of the host that they want to impersonate. Because usually ARP caches are pretty short-lived entries because you don't want this cache to become stale with what's actually happening in the network. So by continually sending these out, you kind of ensure that those machines never actually talk to each other. Cool. Questions on this? So it really goes back to thinking about, at each layer, what types of things can an adversary play with, right? An adversary can play with the source and destination MAC addresses of the Ethernet link layer, right? Yeah?
So if you were using like an intrusion detection system or something like that, monitoring your own traffic, would you be able to tell if someone was sending out and asking out to those ARP replies without any requests?
Absolutely, yes. Yes, so you could definitely, on a busy, large network though, I think it would be more difficult. And intrusion detection systems are always a cat and mouse game because the way we always think about security is in terms of robustness. So if I know exactly how your security system works, like your intrusion detection system, can I still accomplish my goals? The answer is usually always yes, right? So if I know you look for ARP replies in a certain, if I know you only look for responses to replies, then maybe I will, I'll always send the first reply, right? So in that case, maybe you don't know, but maybe now you detect that you got 2 replies. So maybe then I'd work on trying to actually DOS the other system when you sent out your ARP request so that there's only 1 reply back, so that that request got blocked or dropped. There's always kind of interesting ways around things. And you got to think about, an IDS, if if it's going to alert a lot on a lot of stuff, you'll just disable it. So I'd also can do like a boy who cried wolf attack, where I just make it pop up a lot of alarms that are nothing, and then you'll disable it eventually, and then I'll do what I want to do. Yeah.
Is there a way for a detection system to look at the cache and see like, oh, this MAC address is 100 people? Like,
Not necessarily. I mean, it could, but that is not always an indication of maliciousness, because you could have you could want to keep your IP address and get a different like network interface card. Like this does happen a decent-ish amount. I mean, not a ton, but it definitely happens. Or like, I guess a good example now would be like a cloud environment, right? Where you have new systems spinning up that get assigned the same IP address with a different MAC address. Oh, or the other good example is like when connecting to a new network, oftentimes you don't know what your IP address is, right? So when you connect to a Wi-Fi network, you get automatically assigned an IP address by that network. That IP address, you don't know, could have just been used by somebody else. So you need a way for there to be this updating mechanism. But if you think about if I'm an organization and I know 100% everything that's in my network, you could statically put each of the ARP tables in every single machine, which could possibly work. But you may have some annoyed users when things don't work right. Cool. So moving up one layer, we can actually, in a local network, spoof IP packets. So we can pretend to send IP packets from one person to the other, which is actually just a simple extension of this ARP spoofing that we're doing. Because we're really, when we're forwarding this packet from A to B, as C, we're actually spoofing and creating a new packet to make it seem like it came from A, but really it came from us. So we can use this very easily on a local network to spoof packets. So what we can do is if we are 121 and we want to make a packet from this mobile phone to this computer, so from .76 to .14, we can easily create that packet. And we actually don't even need to spoof the MAC address necessarily of that machine, because many times they don't, like we said, at higher levels it doesn't really care about the MAC address, it only cares about the IP address. So from this machine's, from .14's perspective, it looks like this is a packet that just came from this phone, right? So here we can spoof machines, impersonate machines on the network, and send whatever requests we want. What about the reply?
Go back to the actual device.
It would go back to .76. So it all then depends on what this host thinks the MAC address is of .76. So if it thinks that it's ours, then it actually comes right back to us. So this goes, we can just ARP poison that machine, and then we can talk to it, and host 76 has actually no idea this is going on because they never get any packet to the contrary. Cool. All right, moving on up. So moving up to the UDP layer. So, or sorry, to the transport layer. There we go. With UDP is the first protocol we're going to look at. So UDP relies on IP to provide a connectionless, unreliable, best effort datagram delivery service where nothing is guaranteed. Not delivery, integrity, non-duplication, ordering, or bandwidth. Nothing is guaranteed here. It's just like a best effort, like, hey, you want to send this piece of data to another host on the internet, to another host? Great. But it adds, which actually seems a little superfluous, right? Because UDP, is this adding anything on top of IP so far? Is IP a best effort, connectionless, unreliable delivery service? Or yeah, it doesn't guarantee, IP doesn't guarantee delivery, integrity, non-duplication, or ordering, or bandwidth, right? But what UDP and what the transport level both of the transport level protocols actually provide is a nice abstraction called the port abstraction. So the idea is, so I think it's useful to think of maybe the computer as an apartment complex, right? So the address would define what apartment complex you're talking about, right? But an apartment complex, there's many apartments. So what do you need to distinguish where a letter goes to? Yeah.
Like a board,
But back to the
like that, like a physical address.
yeah. So like the address. So right. So every apartment is going to have the same address, right? But how do you distinguish when you're writing a letter to like an apartment? Yeah, apartment number, right? So just give. Oh, sorry. That got caught by the wind. I don't think that was my fault. Yeah, that was good. Watch out, he may have tampered with that. So we need ways to talk to different residents in the same apartment complex. Similarly, we have different applications running on our systems. We need a way to talk to each of them. So this is why the upper levels introduce this port abstraction, which is the idea is you can address different message destinations to the same IP address. So you can have multiple different applications or network services running on a single IP address, and this port allows you to differentiate between them. So this is why you can run an HTTP server, a DNS server, a mail server, all on one IP address, one node, because they have occupied different ports. So each of those applications knows how to talk to each other. So UDP, as we briefly mentioned, it doesn't provide anything you would like in a connection service. So it's mostly used in multimedia because sometimes, like we said, if you're on a phone call and one packet is dropped, you don't care. But if you had to wait for all packets to be delivered to send more, that would add latency and lag. And there are some really important, so actually the most important protocol that relies on UDP is DNS. So DNS is the mapping of a domain name to an IP address, and that all relies on UDP. So going back to refresh, so now we are at the transport layer. So now we're at UDP. And we can see that to do this, so we have 16 bits for a source port and 16 bits for a destination port, a message length, a checksum, and then the data. So this actually is a very minimal header and additional information on top of the IP layer. So how many ports can we have here?
65,500.
Yeah, which is 2 to the 16, right? So 65,000, whatever, 5535 or something. And when we look at this adversarially, the source port and the destination port can all be spoofed and controlled by the attacker. Right? There's no, again, there's no authentication, there's no repudiation. It's just you get a packet and these are the values in the UDP header. And so building up on our encapsulation, so we have the Ethernet layer, the IP layer, and then the UDP in that IP data, where finally we have our actual application level data here in the UDP data. Cool. So we can do, so does the UDP layer add any additional authentication or verification steps on top of IP? What was that?
It has a checksum.
It adds a checksum. So does IP though.
Oh, doesn't it?
Yeah. I'm gonna give you more candy because I'm getting close to the end of the class, so it's gonna start raining. So does it add anything? Is it more secure, you'd say? Who said that?
It's
faceless, so you don't have any,
The spinning is not really helpful.
you don't have any recognition or acceptance, or it's completely stable.
Right, so just like the IP source and destination can be spoofed, the source port and destination port here can be spoofed. Right? Yeah.
It isn't really like a security abstraction, it's more that we're actually sending like packets of data that are logical now, and we can put together in some manner other than just bits strung together. And
Yes.
also it can go as fast as we need it to, since there's none of that change.
Yes. Okay. There we go. Where's I going with this? So what does this mean about all the attacks that we just saw at the IP layer?
Yeah.
It should happen here too, right? We should be able to achieve all the same attacks that we achieved at the IP layer on the UDP layer, because it does not add any other security mechanisms. So we can do UDP spoofing. That's basically exactly the same as IP spoofing. We can send a UDP request to any machine, and we can spoof the to IP address, the from IP address, the to port, and the from port. So as an attacker, if we wanted to spoof a UDP request from this trusted client to the server, we could send this request, and we can put the IP address as the trusted client, and we could put the destination port as whatever the server expects. But what's going to happen to this reply?
There is no reply in some cases.
Maybe there's not, so maybe we just deleted their whole database.
Or we redirected to our website because it's the DNS request free, and then now the malicious content that they're doing.
Yes. Save that for a little bit. We got to do more steps though. So let's say there is a reply from the server. What happens? Where does it go? Yeah.
Go to the trusted client.
It'll go to the trusted client, right? So from the server's perspective, it does not know that this was a spoof packet. All it knows is the IP address source in that packet and the UDP source of that packet. That one was my fault. And the UDP source port. And so it can make a reply, and it will send a UDP reply back to the source IP, which will go back to the client. Right? So as the attacker, do we necessarily see this? Not necessarily, exactly. I think I may have cut too much. It's all right. So if we're on the same local network as we saw, we can see this reply, right? If we're using ARP poisoning. Well, I won't tell you about that. We'll look maybe on Thursday about how this would work in other hops. But just like with UDP, so just like with IP spoofing, we can actually, we can do UDP hijacking. So if we know of a UDP request that is sent from the client to the server, and we want to spoof what here? So let's say it's a DNS request. Somebody's asking, hey, what's the IP address of google.com?
We spoof the server.
We spoof the server's what?
So we pretend that we are the server.
Yes, and we have to do that how? How do we convince the client that we did that?
We change our source IP address key to the server.
Yes, so we need to reply, right? So we need to reply back to the client as if we were the server. So we can, because we can specify whatever we want for source IP and destination IP. So we can say, this is a packet from the server to the client that's a DNS reply. right? But one thing we definitely do have to do is the client, so let's say the client makes 5 or 6 UDP requests to various servers. And remember, this is a connectionless protocol, so there's no notion of we having a connection established. It gets back 4 packets. How does it know what those replies are to what requests?
Are all these requests the same process? 'Cause then
Maybe, maybe not.
You're sending it to different servers, but you send on different ports.
It could be. So the destination, let's put it a different way. So let's say we make 5 requests to a UDP service, one service running on this server. We get back 4 replies. How do we match up those replies to the request? So what's going to be the same in all those packets? Source and destination IPs will be the same. The source port will probably be the same because it will be the port that we talk to, right? So what'll be different? The message may be different, but that's more application specific. But we can actually tell without, we want to do as much as we can at the UDP layer. We don't want to make the upper layer figure things out. Yeah, the destination port. So what we do is the client chooses unique random ports for each UDP request that it sends, and that way the server replies back as a destination port of that same port number, so that way the client can know that this is a response to that request. In this case, to be able to reply effectively to the client, we either have to send, well, if we wanted to brute force it, how many packets would we have to send? We have to send 65,000 packets, so we could actually spoof 65,000 packets from the server to the client with trying every single destination port. And we can cut that down by doing it smart and analyzing servers. Or we could somehow get a copy of this UDP request. So if we're on a local network and we can do ARP poisoning or we can see the traffic here, we can see that request and spoof a UDP reply. So if this is the key reason of when you're on a local network and you are, and the server will reply at some point. So if you're on a local network and you're doing a DNS query for google.com, if I'm an attacker on your network, I can respond with my IP address. And this is kind of fundamentally a problem of UDP and IP stacks. So, all right, there we are.